It's recording now. Excellent. All right. So thank you very much for coming in. You're our first speaker today in this session about buildings. And Anne is speaking about a gallery model for affine flag varieties via Chimney retractions. Thank you, Anne.
Okay. Well, thank you very much for the invitation to speak. I realise my title is probably a bit too technical for the talk that I'm actually going to give. So really, I should probably just call this Chimney retractions. And the main thing I want to do today is to explain what is a Chimney retraction. And I certainly do not assume that you're all experts on buildings. Yeah. I'm going to be switching between a few different applications, so just bear with me for that because I want to show some animations and things like that too. But we'll just start off with the usual sort of slides. So this is joint work with Elizabeth Milicevic, Yusra Naqvi, my former postdoc, and Petra Schwer. And here's the outline of the talk. So I will first explain what is an affine building. This is the same thing as a Euclidean building, the other terminology that gets used. Then I'll talk about retractions. So these are particular maps from the building onto a subcomplex called an apartment. And Chimney retractions are the kind of retraction I'll be focusing on. I'll explain what the connection is between retractions and folded galleries. I'll tell you what these are and what shadows are. And then finally, I'll get to, is everything okay? I'll get to an algebraic interpretation of this, which is the affine variety bit mentioned in my title. Okay. But first off, let's discuss affine buildings. So throughout, I'm fixing an irreducible affine coset system. Now, this is exactly the same thing as a discrete group of isometries of Euclidean space, which has generating set S, the set of reflections in the faces of some simplex, some compact simplex. Okay, so here's an example. Okay, so if you take an equilateral triangle in the Euclidean plane and you look at, so if I just pick one triangle and shade it, and you look at the set of reflections in the faces of this triangle, take that as your set S, that generates a coset group, so a reflection group. And the tessellation I'm showing you here is the tessellation induced by the group action. And so each little triangle here corresponds exactly to an element of the group. If you like thinking about Cayley graphs instead, the Cayley graph is dual to this tessellation. Now these little triangles here, just some terminology for later. So each little triangle is going to be called an alcove. Sometimes in buildings theory, this would be called a chamber, but I want to call it an alcove for today because I want to use the word chamber for something else. Okay, so just have that example in mind, the group of type A2 tilde, and just have that in mind for the rest of the talk. Okay, so a building of this type, so we've fixed our affine coset system, and what is that? So it's a union of apartments, and each apartment looks like this tessellation for the fixed coset group. So we have a bunch of Euclidean planes tessellated by equilateral triangles. Okay, it satisfies some properties, and you can think of these properties as the apartments sort of being like an atlas on a manifold. So given any 2 points in the building, there's an apartment that covers both of them, which is sort of saying you can compare the points X and Y just by thinking about them inside some Euclidean plane. And then the next axiom is going to say that it's not going to depend which apartment you pick there. So the next axiom is that if I have two apartments, there's an isometry from one to the other, so really a simplicial isometry, which fixes their intersection pointwise. Okay. So there are many different ways to axiomatize buildings, and this is just one of them. Now I'm going to switch screen. Just get the right thing up first. So what I'm going to share now is a thing called the Buildings Gallery, which was developed by a guy called Bram Becker. So it's this beautiful web page. So this is a building of, or part of, a building of type A2 tilde. So the apartments are going to be the tessellation I showed you. So we just start with one alcove, and what will happen in the building is as we go out in radius, we're gluing on more and more alcoves, and you see that at each edge there's branching occurring. So if I just stop there and rotate things around, you've now got two alcoves glued onto each edge of the original alcove, sorry. And now we keep on going. Then it gets more complicated. Okay, we're keep going, and that's as much as has been rendered. Okay, so Bram has done everyone a service by doing these renderings. So that, as you see, buildings are these very complicated objects with a lot of branching going on. Okay, so, right. Now, because they're so complicated, one of the main tools for studying them is something called a retraction. And I'll try and explain it in words using these pictures first, and then come back to my slides, because I think the pictures are helpful. So the idea is we're going to map the entire building, we're going to squish it back down onto a single apartment. And why is that helpful? Well, apartments, they're corresponding to coset groups that we understand very well, and they have geometry that we understand very well. It's Euclidean geometry. So if we can map the entire building down onto some apartment in some way that's still preserving some information, then this can be a good way to study structures in the entire building. Now, the first kind of retraction is, so you fix an apartment, we're going to map it all onto the apartment. It's a retraction centered at an alcove in a given apartment. So suppose we consider the retraction centered on this central blue alcove onto just some apartment containing that. So all you're doing, the way this has been rendered really sets up this retraction well. We're just flattening it all down and preserving the colors in this picture. Okay, so that's a retraction. So another way people talk about it is that you stand on the central alcove and you smooth everything down and away from you. So we're retracting onto an alcove. Okay, so that's one kind of retraction of an affine building. I'm going to switch to a different rendering now. Okay, so a second kind of retraction is a retraction from what's called a chamber at infinity. So at infinity, essentially what you're seeing for the affine building is something that looks like this. So infinity means, for example, cat zero boundary. So the parallel lines in your apartments are going to give you a single point at infinity because they're parallel lines in Euclidean space. And so what you're going to see is 3 pairs of antipodal points at infinity, and you're going to see a circle there, or a hexagon if you like, something divided into 6 equal subsegments. But there's still branching going on, it's still fairly complicated. But what you can do is fixing one of these chambers at infinity, so represented by this blue sector here, you can smooth everything else away from that chamber. So in this picture, if you squish everything down according to color, then that's a retraction of the entire affine building onto a single apartment, but now it's a retraction from the boundary. So just to show you a different sort of picture. So in the affine building, you've got, so here we go. So if we think of the blue apartment, so I've got a bunch of other apartments hanging off there along parallel walls. Now, if I'm retracting from infinity on this side, if this is infinity here, then all of these walls fold down and away from that point on the boundary. Okay, and there's going to be several parallel families of walls, and they all fold down away from a given thing on the boundary. Okay? So those are the 2 kinds of classical retractions. We have retraction onto an alcove, and then retraction from a chamber at infinity too. So I'll stop sharing this and go back to my slides now. All right, can you see the slides? Yep. Okay. Yeah. So these are classical retractions. And one thing we do in this work is we formulate another kind of retraction called a Chimney retraction, which is actually a common generalization of these 2. Okay, can you guys see me at the moment? Yes? Yeah. Okay. So what the idea with a chimney, a chimney is also going to be formally some kind of boundary point. Now, previously we had a boundary point, a retraction from something on the boundary which pushed all of these walls the same way. What we want to do now is to be able to retract from something on the boundary which is going to split it, so that it's kind of like parting hair. Instead of everything going the same way, we're going to split it. So some walls go one way and some walls go another way. Okay, so we're retracting from something which is sort of in between those 2 walls, and it pushes everything away from this strip. Okay, so the notion of a chimney, that terminology comes from Rousseau. There's a lot of sort of kind of bad puns in buildings theory. So you have a building and then you have something called a chimney. And for Rousseau, a chimney is inside some apartment, you have some geodesic ray, and you take the what's called a convex closure of that geodesic ray. So all of the half apartments bounded by walls containing that geodesic ray. So it's some kind of strip type thing, but it might be wider than just between two walls. So a chimney retraction, so it's sort of picking off some point in the boundary and it's pushing walls away from it, potentially in two directions. Okay, so what we do is we formalize this. I'm not going to go into any details about the formalization. It involves root systems, which I'm sure some of you know about, but probably not everyone. For anyone who works regularly with buildings, nothing in this formalization should surprise you. And we're using sort of standard techniques. And it's a little bit surprising to us that nobody had written this down before, because it is a fairly natural thing to do with a building. And James Parkinson isn't here, but I could explain it to him in one sentence what to do, and he'd be like, oh yeah. Okay. So, okay, this was first described, and I'm saying described rather than formalized here, for certain Bruhat-Tits buildings. So these are affine buildings coming from algebraic groups over non-Archimedean local fields. These were first described in a paper of, so far as we know, in a paper of Gertz, Haynes, Kottwitz and Weyman from 2010. Their interest was in affine Deligne-Lustig varieties, and I will say something about those right at the end. But there is an algebraic motivation for this. But we do this for arbitrary affine buildings. Okay, now the next, okay, I'm missing a slide. So never mind, I'll just go to my other shared screen. Okay, I'll stop this. Okay, so the next thing I want to talk about is folded galleries and shadows. I think my iPad has not quite the most recent version of it, I'm sorry. Okay. Right, okay, so this is the paper and I'm going to show you a picture with some folded galleries. Here we go. Okay, so a gallery for us is formally it's some sequence of alcoves, possibly including repeats, where each alcove is connected to the next one by an edge. Okay, so we're just drawing this blue line here, but what that really means is this alcove and then this one and then this one and this one, this one, and this one, also including the information of these edges in between. Because if I consider one which is folded, say this purple one down here, this alcove gets repeated and I want to record which side it gets, it's bouncing against. Okay. So it's this sort of combinatorial gadget, but we're drawing these continuous paths because we want to think of a folded gallery as a continuous object. Okay. Now, where are these folded galleries coming from? Well, this shaded region here, this is what we call a sector representing a chimney. So off at the boundary, off at infinity, there's some chimney here. And then you can think of all the galleries in the building which start here and have what's called the same type as lambda. So in a building, each of these three edges of any given triangle has the same type, and the action of the affine coset group preserves type. So the combinatorial information includes the types of the edges which are crossed, and all of these blue galleries are minimal galleries of the same type, so they're as short as you could be to get from this origin up to lambda, or these other images here. And the galleries here are just in a single apartment, but what you should be thinking, and what's true, is that if you take all of the galleries of that given type in the building, so with all the branching going on, and then you apply the retraction from this chimney, what you get in the apartment is these folded galleries. So you're starting with a gallery and you apply a retraction and it ends up possibly folded back on itself or tipped over the entire way. And you get what's called a folded gallery. Okay, so retractions and folded galleries go together. Folded galleries have been studied under various names by various people in algebraic combinatorics, Garçon and Littleman in particular, also Arun Ram. So yeah, they're going to be the connection for us between these chimney retractions and the algebraic information that we actually want to get our hands on. Okay, so now a shadow. So we're thinking of a shadow as, if that's not written down. Okay, I'll just go back to my iPad and I'll write down the definition for you. Okay, so yeah, we can see this now. So we have a chimney psi. I'm using this letter because we're thinking of the chimney as something on the boundary. Then the psi shadow of X is the set of all end alcoves of galleries of type X. So you're starting with a minimal gallery, a shortest gallery from your identity alcove to the alcove representing this group element, which are positively folded with respect to the SI chimney. And all this means is you have a gallery of type X and you've got it by retracting from that chimney. So that's what we call the shadow, because it's everything that sort of gets hit on your way down. Okay, and so what we prove, and I'll go back to another picture in a moment. So one thing we prove is we get a recursive description of shadows. Okay, so this notation here, sorry. Okay, so we have some point on the boundary. We can think of that as being represented by some sequence of alcoves going out. And given any X, once you go far enough out, you can think of retracting from the chimney on the boundary as the same as retracting from some alcove, which is far enough away. Okay, so it's going to have the same effect. So this shadow here is retracting from some alcove YS further out. Okay, so it's saying if you start at Y and then you go to YS, so that's an adjacent alcove which is further out because the length increases, then the shadow of X with respect to the retraction from YS is found by taking the shadow from the previous step. And then, okay, you have a wall H, which separates the alcoves Y and YS. You have RH is the reflection across that wall, and then HYS is this half here. So you have your shadow from the previous step, intersect HYS, so that's some stuff out here, you reflect it back, and now that's giving you the new shadow. Okay, so it's a way to recursively compute shadows. Let me show you a picture. Okay, and I'll go through the picture somewhat slowly because I think that's probably more helpful. Okay. So this one here. Okay, so we're starting with, here's our X, and this is the chimney that we're going to retract from. More formally, this is a sector representing the chimney, and the chimney is this boundary point off here. Okay, so starting here, we're going to step, the Y's are going to step along this sector. And what's been colored is the wall gets crossed at each stage. Okay, so we start with our minimal gallery out to X. Now, if I cross the wall from this base alcove to the next one, then I have to fold back everything that was in the original shadow. So I'm going to take this pink alcove and fold the gallery over here to get this purple alcove. So I folded pink in the purple wall, and now I get a purple alcove. Okay, so that's the first part of my shadow. Then I've crossed this darker purple wall, and now from these two alcoves at the previous step, I generate these two dark purple alcoves here. Okay, I've reflected these two alcoves to get these two alcoves. And I continue, I get some teal ones, then some blue ones, and so on. And eventually, once I'm far enough out here, I'm not going to generate any more alcoves in the shadow because I've gone so far that not everything's already been folded away from the chimney. So this is an example of a shadow here, the shaded alcoves, but this picture's also intended to show you how the recursion operates to compute the shadow step by step. Okay, now let me just get something set up. Okay, so on the next slide, it's going to be an absolute slew of notation, and I will take it slowly and do some examples. So just brace yourselves for that. We're going to now go to the algebraic interpretation. Okay, so this is unavoidable when doing this stuff. Okay, so we have a split connected reductive group. So please just think about SL3. Have some field with a discrete valuation. That's not actually going to be so important to us, really, because everything we're doing is sort of only taking place in one apartment. And so we actually don't care too much which field it is. The field will affect what happens in the entire building, but the apartment's going to be the same for any building for a fixed G, okay? Any affine building for SL3 will have apartments which are this tessellation of the Euclidean plane by equilateral triangles. We have something called the Iwahori subgroup of G of F. So you've probably heard of a Borel subgroup of SL3, that's the upper triangular matrices. And the Iwahori is a sort of affine analog of that, in a way I'm going to try and explain. So in this setting, you have associated to G of F, you have what's called an affine Weyl group. So this is an irreducible affine coset group. For SL3, it is the example we've been working with throughout, AT tilde. The quotient G mod I, so modding out by the Iwahori, is called the affine flag variety. And this affine flag variety, or G of F, has this decomposition which is indexed by the elements of the affine Weyl group. Okay, so you maybe recall that G mod B is indexed by elements of a finite Weyl group. So if you look at cosets of SL3 mod its upper triangular matrices, those are indexed by elements of the symmetric group of 3 letters, in fact. There's also an affine analog of it, and this is called the affine Bruhat decomposition. So in terms of the building, the apartments are the tessellation coming from W, and I, the Iwahori, you pick a base alcove, and the Iwahori is the stabilizer in G of that base alcove. Okay? So the alcoves of the building are in correspondence with the points of the affine flag variety. Okay? You have a group acting on the building, and I is the stabilizer of your base alcove. Okay, so that's where we are so far. Now we pick what's called a standard spherical parabolic subgroup. So example here is these elements of SL3, which have zeros in those entries there. And flip that to get the other standard spherical parabolic subgroup. And this group has what's called a Levy decomposition. So M is called the Levy factor, and I think N is called the unipotent, and this is what M and N are for this particular P. Okay, and then we have a group called IP, which is you take the Iwahori, you intersect with M, and you multiply by N. So this is some sort of Iwahori for the parabolic. Okay, so what does this have to do with anything? Let me go to the next page. So, okay, sorry, I missed one thing. We have, as well as a decomposition with I here, we also have a decomposition for this group IP. Okay, so I needed to say that. So what we have on this slide are two different decompositions of this algebraic group. And a natural question is to ask, when do the pieces of these decompositions have non-empty intersection with each other? Or even better, can you describe what the non-empty intersections of these stratifications look like? And answer is yes, we can. So we have, I just made a typo here, sorry, this, that should be Y. Okay. Yeah. Sorry, let me just double check that. Sorry. Okay, there's no Y, believe me. There's a more general result where there is a Y, but here we just have two lines. Okay, so here, this is the Bruhat decomposition with an Iwahori at the front, and this is with an IP. And there's a bijection between the set of points of this double coset intersection. And okay, so a labeled folded alcove walk is a gallery with some decorations which tell you how it's traveling through the building. Okay, so previously we just had galleries living in a single apartment. A labeled folded alcove walk is really recording where it's going in the building, which sort of flap it goes along. Okay, and so what this is saying is that these mysterious double coset intersections can be got hold of by understanding the folded galleries picture. And the folded galleries, which are positively folded with respect to the P chimney. So given a parabolic P, that actually determines a chimney, okay, in a natural way. And so these chimney retractions and our recursion actually give you a concrete way of computing these double coset intersections. Now, this is not the first time people have looked at these kinds of double coset intersections. For various values of P, so James Parkinson, Aaron Graham and Christoph Schwer looked at some of these intersections and made this connection to folded galleries. Before that, Gaussen and Littleman, before that, MacDonald. It's a bit of a folklore result, these kinds of statements. And we have more general statements too. This is just the one that was easiest to say for the purposes of this talk. And then to finish, I will just say, so since this 4-author paper, Milicevic, Schwer, and I have used this theorem to study what are called affine linguistic varieties, which are important in arithmetic algebraic geometry, I've been told. So this theorem gives a connection between folded galleries and double coset intersections. The Gertz-Haynes-Kottwitz-Reumann paper I mentioned before gives a connection between double coset intersections and affine linguistic varieties. So with those two connections and then doing combinatorial arguments with galleries, we're able to say some things about when affine linguistic varieties are non-empty. And I've gone very fast. I can go back and show you some pictures if you like, but I'll finish there.
Thank you very much for that, Anne. Lovely talk. Do we have any questions from either in the room or from the other participants? Somebody is on mute.
Yeah, I can't.
What's that? Oh, thanks. Yeah, any questions, comments? Silence.
So is if I can ask something vague.
Yeah.
So you've started with very geometric pictures and then we had all the algebra.
Yeah.
And so is it the interplay between the two things that you can make progress?
Yeah. So, I mean, the bulk of the paper applying this is, we show that there exist folded galleries. We construct certain folded galleries, and then this tells us that certain affine linguistic varieties are non-empty. But the bulk of the paper is really combinatorial things with, drawing squiggles in the plane, and and we needed to do this Chimney's work to get that on a sound footing. This would be, I think, a much less interesting result if we didn't also have the recursion, because the recursion actually allows us, says that you can compute things, and we have code to do this. I should have mentioned, we wrote code for this. So.
Okay, and you can use induction or something to prove.
Yeah. So given any particular x and z, with our recursion, we can tell you at least yes or no, is this intersection non-empty, the intersection of these double cosets using our recursion.
Okay. I thought the pictures were great. Are they all done with teaks, or is there a special buildings thing for latex?
So Bram's pictures, I have no idea what he's actually using under the hood. My pictures, I use Inkscape. I import a picture of the tessellation and then I just draw.
Fair enough. Yeah. Okay. Yeah, that works.
So yeah, I'm not coding, I'm just drawing.
Okay.
Okay, that was going to be my question. So that could, in principle, be coded up, all your galleries, and then make the connections with the algebraic part?
Yeah.
Could you say a little bit more about what a chimney is? I didn't.
Yeah, okay. I was trying to avoid the technicalities, but let me get some paper up now.
Oh, okay.
Right.
That's technicalities, but.
So, okay, so we've got, so we've got our root system, and so then we've got a base for the root system, so these are the simple roots. And so if we choose some subset of the indexes of these, and then what we call the J chimney. So formally we defined it as a collection of half apartments. I'll explain which collection. Let me draw the picture I usually do. So type A2, we've got, so this is alpha 1, this is alpha 2. So suppose I take J is 1. Okay, so what we're going to include is, so these walls have labels. So this is H alpha 1, 0, this is the color, this is H alpha 1, 1, H alpha 1, 2, etc. And then similarly with alpha 2. So what we're going to include is all half apartments on the anti-dominant side of H alpha K or I not in J. So what this means is we include all the half apartments sort of below this family parallel walls. And so this will be H alpha 2, 1, this is H alpha 2, 0, the black one. Okay, and then half apartments, H alpha J. So this is going to be the negative side of that one. K for K less than or equal to 0, positive side H star K for K. Okay, so this is the formalization you asked. So what we take is for the alpha 1 walls, we're taking sort of this side of this one and then the upper side of the blue ones. So this is a way of sort of formalizing. We're getting this little strip between the 0 and the 1 walls for alpha 1. And so this, in a sense that can be formalized, does pick off a point in a certain boundary. But really we're thinking of the chimney as this collection of half apartments, and it's represented then by shading some region between these walls in the dominant sector. But we're thinking of the chimney itself as some collection of half apartments to pick out this region. And then retracting from here, what we do is we show that if you want to know what the retraction does to any given point X, you can go far enough along a representative sector and do a retraction from an alcove on that representative sector. Does that answer the question a bit, George?
A bit. So you said this is a common generalization of the other.
Yeah. Okay. So if you take J to be the empty set, then what you're getting is a retraction from an alcove, because you're going. Sorry, other way around. So if J is the empty set, you're actually going to be retracting from a chamber at infinity, because you're not splitting the direction on any of the walls. Each parallel family of walls, everything goes in the same direction. So you're picking out the same side half apartment for all of those. And if J is everything, then for every parallel family of walls, you're picking out a strip exactly between them. And that's actually going to pick out a unique alcove.
Right.
But the sort of, the new stuff is the strip in between. So that's why I was emphasizing.
Right. And if it's, what is it? If it's empty, it's something at infinity.
Yeah, there's a paper of Petra and Schwer where they talk about the combinatorial compactification, or combinatorial bordification, in fact, of buildings. I find this paper hard to read, so we decided not to exactly adopt their approach, and they're also doing general buildings, and we're just doing Affine, where you've got some additional language available to make it easier to say what is happening. So yeah, a chimney does correspond to a point in the Petra-Schwer bordification or compactification.
Right. But where's the where is the information about the alcove in the case when J is the whole set? How do you select an alcove, and how do you select the point of infinity in the case?
Right. Okay. So yeah. Okay. With just 2 elements. Okay. So it should have also. Yeah. Okay. I missed. Okay. So really, I didn't say this quite correctly. So. This statement here should be H alpha K for alpha root in N. So N is the unipotent. So the family of walls that I haven't drawn but should have are these horizontal ones. These are the alpha 1 plus alpha 2 walls. And you pick the anti-dominant side of all of those 2. Okay. And then, sorry, all of those walls together will pick out a unique alcove.
Right. Okay.
If J is including everything. And that's a J chimney, and then you can act on a J chimney to get any chimney just by acting by W.
Right, okay, that helps a bit. I still need to think about it a bit more, I think.
Can you retract onto these in the non-discrete case as well?
We don't know what to do with the non-discrete, because it very much depends on the walls being a discrete set. So, yeah, and like, yeah, the Petra-Schwer thing is also very discrete because they're thinking about sequences of alcoves. So,
right.
Yeah, so I'm not sure if it even makes sense for non-discrete.
I'm asking because your 2 boundary cases, of course, do make sense in the non-discrete case.
Yeah, but this, I mean, yeah, it really depends on sort of knowing what to do, doing things differently on two sides of distinct walls.
Right. Thank you.
All right. Any final questions or comments? Otherwise, let's thank Anne very much for that talk.
Okay.
All right, I think we can stop.